Our world is filled with a vast variety of different things: plants, animals, the sea and air, rocks and minerals. Yet everything is made of atoms so small they're invisible. Combinations of atoms form these larger, varied objects. Energy is certainly involved in bonding atoms, but how? If there is an interatomic glue holding our world together, what's the nature of that glue? Intriguing and important questions, because nearly all the substances around us and within us are held together by chemical bonds.
Everything is made of atoms. But the building blocks of this world are groups of atoms, big or small in number, connected up to each other. So in this flask of water, there are 10 to the 24th or so water molecules, every one of them H2O. In every one, an oxygen connected up to 2 hydrogens. In this salt, there is a vast ordered array of sodium and chloride ions. We've got to figure out what it is that holds atoms together in salt or in water. The key to chemical bonding is this marvelous periodic table of the elements and a knowledge of the electron configurations of the atoms, in particular those of the noble gases like helium or neon. The noble gases are chemically inert. Why? Because they have a filled s and p electron cloud. Now, with very few exceptions, there are no compounds of the noble gases, but everything else in the periodic table, arsenic, copper, indium, nitrogen, sulfur, nickel, these do form compounds. They do so by trying to achieve the stable electron configuration of the noble gases. There are at least 2 ways to do that.
The elements in compounds are held together primarily by ionic or covalent bonds. And the basic rules governing how these bonds form are, first, atoms lose, gain, or share electrons to complete their valence shells. And second, electrons tend to exist in pairs. Only the 6 noble gases do not readily combine with other elements because their valence shells are already full. Making and breaking these chemical bonds is chemical change, and when chemical change occurs, energy is involved. It might take a lightning bolt or something as complicated as algae to break a chemical bond. What exactly are these bonds and how do they form? Electrostatic attraction of oppositely charged particles, ions, forms one type of bond, called ionic bonding. How do ions form? Let's look at an alkali metal, sodium. A sodium atom has 1 valence electron. Its energy level diagram looks like this. Very little energy is required to lose that electron. The outer shell is now full. A positive sodium ion has been formed, smaller than the atom. On the other side of the table, a chlorine atom has 7 valence electrons. Energy is given off when it gains an electron, filling its valence shell, forming a negative chloride ion. When sodium and chlorine are brought together, one gives up an electron, the other accepts an electron. They react, producing an ionic crystalline solid, salt. Energy is involved, as demonstrator Don Showalter explains.
Now, what would happen if we would mix together sodium that wants to lose an electron with chlorine that wants to acquire an electron? Let's see. In this beaker is chlorine gas. You can see the green color that's in there. That's quite a poisonous gas. What I want to do is to heat a piece of sodium metal. So I'm going to put a piece into this glass spoon. I've got to melt it a little bit. So get it in the bottom there. Get it nice and molten. And put it inside here. And let's see what happens. That's quite a reaction, huh? A lot of light. It gets more and more intense. There's a white powder that's forming in there. And certainly the reaction is giving off a lot of energy. Now, once it calms down, let's see what it forms. There's a white crystalline material that is formed on the side of the beaker. That's sodium chloride, regular table salt. What we have done is to take two elements that are quite dangerous and combine them into a substance that is essential for life.
Sodium chloride, table salt, is a member of a huge family of salts, all crystalline solids. The electrostatic forces between the oppositely charged ions holds them together in the crystal. The electrical charge is evenly distributed over each ion, so ions of opposite charges are attracted from all directions. In sodium chloride, each chloride ion is surrounded by and holds 6 sodium ions. Each sodium ion is surrounded by and holds 6 chloride ions. This results in a rigid, ordered pattern of alternating positive and negative ions. NaCl is the formula of sodium chloride. It implies there is 1 ion of sodium for each chloride ion. That 1-to-1 ratio of the ions exists throughout the cubic crystal. Dr. Jeffrey Post, a crystallographer for the Smithsonian Institution, studies mineral crystals like salt.
In fact, if you were to take a magnifying glass and look at the salt crystals from your salt shaker on your dinner table at home, you'd see that each of those little crystals looks exactly like this crystal, but just on a much smaller scale. And we've taken some crystals and looked at them on the electron microscope, and even at that scale, magnified hundreds of thousands of times, the crystal shapes are exactly the same cubic shape. That's an inherent property of this structure.
The lattice structure formed by the ions gives sodium chloride and other salts distinct properties unique to ionic compounds.
I have 2 crucibles. Both of them contain white crystalline solids. They look very much the same. However, one of them is ionically bonded. If the way substances are bonded together give them different properties, we ought to be able to test that. One way to do that is to see if they conduct electricity. All right, we can do that by using this sort of setup in here. Light bulb and electrode system. Let's turn on the electricity and nothing happens. Well, sure, nothing's going to happen. The circuit's open. Let me show you what happens if I close it with this screwdriver. See, the light comes on. How about this one? All right. Well, instead of using that screwdriver, what if we would lower the electrodes into the substances? Test the conductivity that way. I'll lower them in there, and look what happens. Nothing. The light bulbs do not light up. Well, if one of them is ionically bonded, maybe because in the solid the ions aren't free to move around, what if we could help it by melting it? Oh, I hear something happening. Oh, look, it's getting a little brown. I see some liquid coming around there. I've got all liquid, and this does not conduct electricity. So in the molten form, this is a non-conductor, non-electrolyte. But let's see what's happening over at the other crucible. Well, I'm heating this one, and I have to heat it really hot. It looks like in order for anything to happen. Oh, here we go. Here we go. The light bulb is lighting. The bulb is lit. It must mean now that as we melt this substance, it conducts electricity. So what we see is that this substance in this crucible is an electrolyte. The substance over here is a non-electrolyte, doesn't conduct electricity. Let's do one more test. I have two beakers here, each with a pair of electrodes in them. The electrodes are nice and clean. I'm going to put in there some distilled water, pure water. Water into this one, and water into this one. Okay, now let me turn on the electricity with these switches, and let's see what happens. Nothing. Pure water does not conduct electricity. Now, into this beaker, let's put some of this white solid number 1. Oh, and look what happens. The light comes on. When solid number 1 dissolves in water, it conducts electricity. It is an electrolyte. Let's try white solid number 2. Looks pretty much the same. Put it in there. Nothing happens. Maybe a little more? Nothing. Solid number 2 does not conduct electricity. It is a non-electrolyte. Now, what do you think these two solids are? Well, solid number 1 was ordinary table salt, sodium chloride. And solid number 2 is ordinary sugar.
Salt and human history are closely linked. Ancient people understood its value to life itself. Salt was once as valuable as gold. Good people are still the salt of the earth. Today, we produce nearly 40 million tons of sodium chloride a year, with half of it coming from caverns like this one, deep beneath the Louisiana Delta. The rest of our supply comes from huge evaporating ponds or from salt wells. Very little of this salt actually reaches the table. Simple salt is needed by the chemical industry. Chlorine, sodium hydroxide or lye, and sodium carbonate are all made from sodium chloride. And salt is needed by most living things. Cows seek salt instinctively. Whole herds can be moved by simply moving the salt lick. In mammals, salts are practically all dissolved into solutions of ions in bodily fluids. The concentration of the proper ions must be maintained because that concentration actually affects the cell membranes. Other common salts are calcium chloride, which is spread on streets to melt ice, and stannous fluoride, the salt of tin and fluorine, which is used in toothpaste. These different salts might have different crystalline structures. The ion ratios and sizes may be different.
This is a calcite crystal. The edges come together at an angle. They're not perfectly squared off like they were in the salt or in the halite. And so this is a property of the basic structure of calcium carbonate. The calcium ions and the carbonate ions stack together and they repeat in 3 dimensions millions of times to build up a crystal. But because of the different shape and the different charges of the carbonate molecules and the calcium ions, these stack together energetically in a different manner. And so the result is a crystal shape that looks quite different from that of the halite.
This table salt is our most commonly known ionic compound. But ionic bonding is not the only way that atoms can combine. Most substances around us are molecules held together in another way. Take this salad oil or vinegar or any molecule in my body. The atoms in these molecules are held together in a different way by covalent bonding.
Covalent bonding is the most common type of chemical bonding that holds atoms together in molecules. Molecules are electrically neutral combinations of different atoms. Unlike ionic substances, which are solids, molecular substances can be solids, liquids, or gases. To understand covalent bonding, let's begin with the simplest element, hydrogen. Imagine two hydrogen atoms, each with one proton in the nucleus and one electron. Both atoms have the same energy and their valence shells are not complete. As they move towards one another, the electron clouds begin to overlap. They start sharing electrons. A molecule is forming. When the clouds overlap, the electrons are paired together, shared. The valence shells are complete, and a covalent bond has been formed. On the Sun, at high temperatures, hydrogen can exist as separate atoms. But at far lower temperatures here on Earth, hydrogen exists as molecules, which have lower energy than the two single atoms. Here, that's the preferred natural state. So, as the two atoms move together and the electron clouds begin to overlap, forming the molecule H2, the energy within this two-atom system decreases. Whenever a covalent bond is formed, energy is released. Where does the energy go? It's released to the surroundings. If controlled, that energy can move mountains. In certain compounds, chemical bonds are weak and can be easily broken, freeing the atoms to reform into molecules with stronger bonds. When they do, an enormous amount of energy is released. Most conventional explosives contain nitrogen atoms weakly bonded to other atoms. Why nitrogen? Because when nitrogen forms its molecule, N2, the atoms will share 3 pairs of electrons. The bond formed is one of the strongest known, and the energy released in the process makes nitrogen-based explosives unique, as Don Showalter will demonstrate.
Now, we've seen a little bit about nitrogen bonds, how 2 nitrogen atoms will combine to form a stable N2 molecule. Iodine, a member of the halogens family, will also form a stable diatomic molecule. Now, you would think that the electrons in the nitrogen atom would be easily shared with 3 iodines. And you're right. Now, this small brownish pile that you see in front of you is nitrogen triiodide. Nitrogen bonded to 3 iodine atoms. Nitrogen doesn't need much encouragement to go back to its elemental form, N2. And when it does that, many times the energy release is quite surprising. Let me show you. I'm going to protect my ears by putting some cotton in them. And I'm going to initiate this reaction by the touch of a feather. Let's watch. Wow! What a reaction, huh? The nitrogen triiodide went to nitrogen, N2, and iodine, I2. You saw the purple iodine cloud that came out of there. Now, this strong tendency of nitrogen to form that N2 bond has many applications.
Explosives have impacted civilization in peace and in war. Tunnels, canals, excavations, and roadbeds were all made possible by these high-energy explosives. The trinitroglycerin of dynamite and TNT made mining more efficient. But the explosive of choice in today's blasting industry is a fertilizer.
The white stuff that's going in there is a base load of ammonium nitrate and fuel oil.
Ammonium nitrate, another nitrogen compound, is a fertilizer farmers use on their fields.
Now these holes will go off in a timed sequence.
Lynn Corson is a research fellow at ETI, the company supplying the explosives for today's shoot.
What will happen is that the charges in front will begin moving the rock out of the way so that the charges in back will not have as much rock to move out.
Were you
Each hole is filled with the ammonium nitrate fuel oil mixture and a primer of TNT. In a fraction of a second, there will be millions of chemical bonds breaking and reforming to produce an explosion. Four and a half tons of ammonium nitrate were used in blasting away this rock cliff. When any covalent bond forms, energy is released. The same amount of energy is needed in order to break that bond. This is something nature does every day. There is nitrogen in all living things. Muscle, hair, and DNA all contain nitrogen bonded to other elements. But 80% of the atmosphere is nitrogen molecules, held together by strong triple bonds. How do living things get the form of nitrogen they need? Lightning helps. It has enough energy to break apart nitrogen molecules, which then react with oxygen in the air, eventually forming nitric acid. This natural acid dissolves in rain and falls to Earth as a dilute solution. There, it is absorbed and metabolized by plants. Some plants, though, convert molecular nitrogen in a different way. Soybeans and other legumes, like peas and peanuts, host a unique bacterium in their roots. It is this bacterium which converts the nitrogen molecule into a nitrogen compound, ammonia, which the plant can then use to make amino acids. Exactly how the bacterium works is the subject of vigorous research. From the U.S. Department of Agriculture, Don Keister.
This is one of the very unique enzymes in all of nature because it is the only solution that nature has come up with for biologically reducing nitrogen.
The soybean and the bacterium have a symbiotic relationship. The plant houses and feeds the bacterium, and in turn, it receives the nitrogen it needs. But not all plants can host these nitrogen fixers. They have to rely on rain and manufactured fertilizers like ammonium nitrate, and they're expensive. As the world's population grows, so does the demand for food, which depends on nitrogen fixation.
We are currently using something like 300 million barrels of oil per year in this country alone to produce nitrogen fertilizers. We, for instance, predict that we're going to need to double the food supply over the next 20 years. Where is that energy going to come from? Where is the fertilizer going to come from?
For feeding the world, there are two basic options. We can either produce more fertilizer at greater cost and some risk to the environment, or we can create new varieties of nitrogen-fixing plants. Both options are being pursued worldwide. To review, except for the noble gases like helium and neon, which have full valence shells, everything around us is chemically bonded. Ionic and covalent bonding are the two main ways which elements can bond. Ionic bonds form when atoms either give up or acquire electrons. In the process, they become positive or negative ions, which attract one another, producing salt crystals. Covalent bonds are formed when two or more atoms complete their valence shells by sharing electrons. As atoms form molecules, energy is released, so molecules have less energy than the initial atoms. To break molecules apart, back into their constituent atoms, energy must be put back into the system.
My own research actually has to do with bonding in molecules. What I want to know is why a molecule has the structure that it does. Let me tell you a story of something I did a few years ago. There's an important class of molecules called organometallics. They have an organic piece and a metal atom. One day, a German group made a new one of these, trisethylene nickel. It has in it ethylenes and a nickel atom. Now, when they made it, they didn't know its shape, its structure, whether the ethylenes were standing up like soldiers, or if they should be lying down the way they are in this model. Why does it matter? Well, the shape of a molecule is important in defining its properties. Molecules close to this one were active as catalysts in making polyethylene. But that's not the reason why I was interested in them. I just wanted to know their geometry. Together with my coworkers, and looking at the way that the electrons move in this molecule, we were able to predict that the ethylenes should be lying down the way they are now. Within a very short period of time, a group in England confirmed this prediction on a related platinum-containing molecule. You can see that this is a problem in molecular architecture. Chemical bonds are connections between atoms of a definite strength, a definite length. They make molecules out of atoms. But knowing the bonding in a molecule is not sufficient. Molecules also have a characteristic shape, a structure, an architecture, which we will see in the next program.